Hey, what's going on, guys? Games here. In this video, we're going to implement Raycasting algorithm, and instead of diving into the math, I would rather emphasize the practical implementation. So we'll go step by step, and I'll try to demonstrate the most essential parts of the algorithm. I'll try to break it down as much as I can. So eventually, you will come up with not the math, but the visual understanding of how the algorithm works, and observing all the math being involved within the algorithm from the visual perspective, not from the theoretical mathematical perspective, but from the visual perspective instead. And in that case, it turns out to be really simple and straightforward. So if you're interested, without further ado, let's actually start. Okay, so let's define a few more constants. So here I say field of view equals to math.pi divided by 3. Okay, so this value is in radians because we're working with radians. It should be somewhere around 60 degrees if I'm not mistaken. And also we need the half field of view, and this would be equal field of view divided by 2. Pretty simple and straightforward. And also we need to define the player angle. So what the player angle is, it would be equal to math.pi. This means that it just looks up. Okay. So player angle would be represented as the line where our player is looking at. So let me just open the terminal in the current working directory and say python3 part2.py. So currently we have just the map and our player being marked as this red circle. So now we need to see where exactly the player is facing. So where is kind of like his face and where is the direction he's supposed to go. Okay, so I want to add a few more lines to draw map function for this purpose. And when I do this, it would be visually clear what in particular the player angle is, how it works, and what in particular the field of view is and how it works as well. So let's do it. So let's say, so here I want to say the direction player, let's say just player direction, and let's say just draw. Okay, so I can say pygame dot draw, and I want to draw the line to the window, the color, let it be green, and now two tuples, and also let's give it 3 pixels width, or maybe it's not exactly in pixels, but just to make it a bit more like thick line here. So the first here we need to specify the player X and player Y coordinates, so the starting points where the line comes from, and here we'll specify the points where the line eventually comes to. Okay, so here we can simply say player X and player Y, whatever coordinates we have, and here is where the only math application occurs. And we would be reusing this in the Raycasting algorithm on its own in order to move our character on the board as well. So whatever place we would be using math at comes from this exact place. So here is just more didactic. It's easier to see what in particular we want to be doing. So I just need to say player X plus math.sin and the angle of the player, so player angle. Okay, and let's give it a bit more space here, so let's put it right over in here. Okay, and here for player Y we need to say plus math dot cosine in this case and player angle. And this is the entire math for the entire Raycasting algorithm, believe it or not. I mean, it's in the most simple form at very least. Okay, so we've just defined the starting coordinates and the end coordinates. So let's have a look at our output. So you see, like, it's very miserable here, so we can't really see the direction. And in order to give it a more clear, in order to make it more clear, we just want to multiply this by a certain constant. Let's give it like 20. And if we do this again, now, okay, excuse me, invalid position argument. Oh, what have I done? What have I done? Obviously not. Multiply by 20. And here we go. So now you see the direction shows up to, like, we go in like forwards. Well, it's too small. Let's give it a bit more. Let's make it like 50. Okay, let's make it 50. Okay. And now it's much better. And now, guys, what I've just done, so we had a short line when we had, say, this kind of constant of 20, and now I gave it a constant of 50, and the line grew up, so now it's longer. So what I've just done is the essence of the raycasting algorithm. So I've just casted the ray forwards. So let's say we're gonna be adding like a very small portions, like this is called depth, how far. So the length of this kind of line is how far it can go, how deep it can go. So we would be multiplying here in the raycasting algorithm itself. We would be multiplying this target position X and target position Y by the depth. Okay, and in that case, this would result in this line being longer every next iteration. And then we will need to do this not for the only line, but for all the lines within the field of view. But just to give you an idea of what the field of view is, let's actually draw our field of view here as well. So here, the next thing to consider, we want to draw players, player field of view. And here I just want to grab this piece of code and paste it in. So now the difference is that, so we need to make two lines. So first, in order to get the leftmost part of the field of view, we need to say player angle minus half and field of view, and the same is here, so minus half and field of view. And now let's have a look at the output. Okay, so I just want to close this part, this window. Okay, yeah, let's go for it. So now we have, I'm sorry, this wasn't leftmost, this was the rightmost, but doesn't matter at the moment. It would be the leftmost. Well, that's because we have the plus sign here. If we make it minus sign, in that case, we will have it from the opposite side. Okay, it's better, it's clear, it's way more clear to explain when it comes to the rotation. So first, let me just draw the entire field of view here, and then I'll comment this out and walk step by step just to give an idea how this plus and minus signs affect the output. Because for me personally, this is the only way to learn some complicated math related things, just to visually see what changes does the code produce every next moment. So yeah, here is the field of view. So we have, like, we can see to the left of this line, and we can see to the right of this line, but we can see within this range. And this here the rays are not casted to the very end of the map, they just casted to the limited kind of space, but the actual rays would be casted within this range. This is the field of view, this is the field of view. So within this range, we would be casting rays like this, and we end up right over in here. Now regarding the directions, it's another incredibly important thing to consider. So at the moment, let me just comment out these lines. So we'll keep only, we will only keep our direction, like player angle, literally where the player is looking at. Okay, and now let's add some user controls. So get user input, let's say. So I need to say so let's say call it keys equals to pygame dot key dot get pressed. Okay, and now we want to handle the user input, handle user input, and let's say if keys indexed by pygame dot k left. In this case, we want to say player angle minus equals 0.1. So remember, we're working with radians, and for so this would represent turning camera kind of like to the left, turning the field of view to the left, and here we want to turn to the right if we press on the right arrow key. So I'm going to be working with arrow keys here. Okay, and here we go. So now if I see, like, the problem is that now I press left button but it turns to the right, and now I press right button and it turns to the left, and it's not really that great. And that's the reason, and in order to fix this, and that's the reason why we want to use minus right over in here. Okay, and now I press left, it goes to the left, I press right, it goes to the right. Okay, and now let's bring our code back. Exactly the same, but I just want to change plus to minus. So just to give you an idea where this minus comes from, because when I saw this initially, I had no idea why this minus sign, not plus sign and things like that. So it wasn't really clear for me. And now you see it, now the leftmost, as I've mentioned in the beginning, so I said this would be the leftmost kind of part of the field of view. So when it comes to be minus sign, it starts being the leftmost. Okay, so this is the leftmost, as been mentioned, and this one is the rightmost, but don't forget to change the sign to minus here as well. So now if we have, okay, run this again. So now we have our field of view being rotated with a ray angle. So here is another little disaster. So you see, like, it doesn't update the background here, and if we extend the rays like further on, it would be drawing here as well. So let's handle the background update here as well. So probably I can put it in drawing the 2D map. Yeah, I think this might be done. Or yeah, alternatively, yeah, let's say. So where do I want to, yeah, update, I think here is okay, update background. So I just want to draw a rectangle, drawing rectangle to the window. The color would be black, and start at 0, 0 XY, and then we want half screen, so it would be, well, later on we can, well, okay, first, well, I could make it the full screen, but I just, you just remember that this part is dedicated to the map, while this part is dedicated to the future 3D projection that we're about to implement. But here we will want to distinguish the floor and the ceiling. So for now, I'm not going to be touching this. So let's say screen, yeah, so we can use the screen height parameter here because we only want the half. I just don't want to say like screen width divided by 2. It would be more exactly, but it's slower because I want to have as I don't really want to have many divisions and multiplications within this, so because later on it would be slowing down the entire engine. So just trying to avoid that sort of a thing. So screen height and screen height. So literally 480 and 480 pixels here as well. And just to make sure that it's working, let's make it white first, so we'll see it in the grid. Okay. Okay. Okay, so you see, like, now we see the background being updated, and no more issues with drawing on the background and not being updated after. So we can drop back this to zeros. Okay. and let's have a look. So now we can turn around, but no disaster is happening. Okay guys, perfect. So now the heart of the algorithm on its own. So without further ado, so here down below the draw map, I would say I want to cast, so this would be the Raycasting algorithm. So Raycasting algorithm. And now I've been discussing this sort of a thing for such a long time, just because what we're going to be doing within the Raycasting algorithm is exactly the same thing what we've been doing here. So this is absolutely essential. Okay, and I want to define the function called cast rays. Okay, let's pass for a while and let's put the function after drawing a map. So Raycasting. So let's say like apply Raycasting. Okay, and here I want to cast rays. Okay, cast rays. Great. So the very first thing to consider now, we need to define the starting angle. So the starting angle is the leftmost line of the field of view. So just again to show you this. So start angle is this kind of direction. I want to say the start angle is this line, but angle is not a line, but you know what I mean. So we need this sort of angle. Okay, so I can say start angle would be equal to and now this one leftmost, so player angle minus half minus half of field of view. Okay, and then we'll have a loop. So here we want to define leftmost angle of field of view, and here we want to increment angle by a single step. So it would be like starting angle, then plus step, 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 plus step. Now if we want, now we need to know this step, right? So first let's say start angle plus equals, let's call it step angle. And now let's go to the global definitions, and here we need to define the step angle as field of view divided by casted rays. And now casted rays is another constant. So casted rays is the number of rays that we're supposed to be having within this field of view. So like here, let's say now we have only 3 rays being casted, so 1, 2, and 3, but we want more rays. So the more rays we have, the better 3D projection will obtain as the end result. Now the best ever possible solution is to have the number of rays equal to the number of pixels in the width of the screen that we're supposed to be rendering. So not the entire screen, because it's not going to be the projection for the full screen, but only for the right part of the screen for this one. So here we have 480 pixels. So in my dreams there would be like 480 rays, but it would be slow, and bear in mind the fact that I have my video recording software working and all this stuff. So we can just take less rays. So I'll take 120 rays, and then we'll provide this scaling, the constant to scale the screen width to the number of our casted rays. So it would be more clear when it comes to rendering the the 3D projection, projection screen. Okay, but at the moment we just know that here we will have exactly 120 rays being casted from the player and to the outer space. So here I want to say the casted rays is equal to 180 and 20. Okay, so now let's get back to to this algorithm. Okay, so now we need to loop over casted rays, and I can simply say for array in range and casted rays, so 120, but casted rays, I'll use the constant here. Okay, and now we want to cast a single ray step by step. So by saying step by step, I mean what I've already been trying to explain. So let's run the code again, so just to give it more sense. So here, let's say that this is this is one step, another step, another step, another, and so on. So what do we have? Well, we can take the step being equal to different kind of like values, but we would be going pixel by pixel. It's not the it's the worst, probably from the performance perspective. This is the worst possible way of doing things, but this is the most straightforward and clear way of doing things. So we can so now we can say for depth in the range of the maximal depth. And now to calculate the maximal depth, so let's define another constant right over in here. So we have the map size and we have the tile size. So we can calculate the maximal depth. This is gonna be the integer, by the way. It would be map size, so this 8 multiplied by the tile size, and we should have 480, by the way, because if we just multiply the screen by 2 and we have this 480 and then divide by map size, so if we do the opposite multiplication, this so I could have said like max depth equals to screen height, but just to give it a bit more didactic value, I would say map size multiplied by tile size. And just to make sure that my calculations are correct, let's print the max depth, and it should be 480. So max depth. Sorry guys, I'm extremely bad in math. You can't even imagine how much. And I really need to check every single step where that involves calculations, because otherwise, yeah, we have 480, which is absolutely fascinating. Okay, so at very least, I didn't fool you in this case. Okay. Okay. What else? Okay, so now we need to define the target X and target Y coordinates. So if we drop back again, like, I'm sorry. So we have this player X and player Y, and and the point where the ray stops would be the target X and the target Y. So we need to calculate this. And in order to calculate this, we use exactly the same math we've been using here to draw the player direction and the field of view. So, but we instead of multiplying this by the certain constant, we would be multiplying this by depth. So I take this, copy, and here I can say target X equals to, okay, and now we need to take all of this stuff and multiply it by depth. Sorry guys, yeah, obviously, yeah, we need to multiply the sign by depth, not the entire stuff. Sorry for this. I really suck in math, I'm sorry. Okay, and here target Y would be equal to player Y and math plus math, and now cosine. Okay, depth. And now before anything else, so before detecting the collisions of the ray and the wall, first let's actually print the line, just like we did right over in here. So okay, and yeah, first here we want to get array target coordinates, and here we want to draw casted array. So this is the heart of the entire algorithm. Okay, so here I just can say target target X, and here I want to say target Y. I don't need them to be thick, so this should be just fine. And if I did everything properly, it now should draw like many rays, like every ray of 100 rays should be casted to the screen. Well, yeah. Okay, the moment of truth, guys. So okay, yeah, it's slow as hell for some reason, but I just can't see. Well, the matter that it is slow is good sign, but I just can't get. So hold on a sec. Okay, what a dumb I am. So obviously we need to do this with the start angle, with the current angle we're incrementing. Oh man, sorry guys. Oh yeah, no, this should work. Okay, better, but not perfect yet. Okay, and yeah, obviously, yeah, just was incrementing the angle in the wrong place. Okay, so please. Okay, this is it. Yeah, now it's slow as hell because we don't break when. Yeah, I'm sorry guys, it's just gonna be slow as hell. So just to demonstrate you this, you see like it's starting, but it's really slow. Let's just break out from here. So let's make only like, let's say 10 rays for now. Okay, because otherwise it would be slow as hell. Okay, so only the first 10 rays. Okay, but as soon as we drop the rays, if they hit the wall, it would be much faster. So let's implement that as well. Okay, so the next step to consider, we need to convert this target X and target Y coordinates to the index that we would be indexing our map by. Okay, so the formula to get the index would be just as we used it before, so row multiplied by the map size and plus the column, but we don't have rows and cols, we have the X and Y coordinates. So we can simply say target Y and divided by the tile size. Okay, and then we want to multiply it by the map size. Okay, and then we want to say plus and target X to convert this to column divided by tile size. So I can even say, well, let's break this down even more. So let's say convert target Y coordinate to map row. This would be more didactic, I believe. So let's say row equals to, and this stuff. Okay, and now let's say X, Y coordinates to map col and the row. So now let's say column equals to target X divided by the tile size. Okay, so we have this called tile size. Yeah, this is it. Good. Okay, and now we want to calculate map square index. Okay, so square would be equal to row multiplied by 2, sorry, multiplied by map size by 8 by map size plus column, And now we want to match. So, well, first of all, let's before anything else, let's just print our square, and this should be in range of our our map. Okay, so sorry for breaking down that much, but when I was doing this initially, it was completely unclear how can we convert this visual array to the coordinates of the map. So that's the reason why I try to put extra effort to showcase this. Okay, so divided by, okay, so you see, like, okay, and yeah, obviously we need to make them integers as well. Yeah, so this would be integer like this, and this would be integer as well. Save. Okay, and I'm slightly confused by the fact it goes for negative values as well. Okay. Okay, guys, yeah, just forgot obviously to break after we find after we hit a wall. We don't want to do anything else. So in this case, we'll no longer have negative numbers there, so it won't be index out of range exception any longer. So you see, like, always the positive numbers. And now the reason why it's slow as hell is because we are drawing our arrays in a little bit wrong place. So we actually should do this right before the break. Okay, and at this indentation. Okay, so now we finally have working properly. Okay, so now we can make the number of rays back to 120, and hopefully it would be working properly. Okay, so let's go back to casted rays like this, and yeah, here we go. Hold on a sec, why is this still slow as hell? Okay, it happens just because we're printing the squares, so if we get rid of this, it now would be working normally. Okay, so finally we can rotate the camera left and right. And now the very last thing to consider, we need to make our character moving. And we don't want it to move like just the absolute coordinates like X or Y, but we want our character to move along the ray that is being casted, along the player angle to be exact. And we're going to be using exactly the same math here. So it's the third place where exactly the same math is being used. So let's go and implement this, and then I'll quickly I'll make a quick summary. Okay, so if case and pygame dot k up. In this case, we want to do two things. So I want to say player x plus equals minus sign math dot sign and player angle. Okay, so exactly the same thing. And here player y plus equals math dot cosine and player angle. Okay, and now I want to do the same but for the down key and just the opposite direction. So minus equals, and here we go. So yeah, now we can move, but you see, like, we are moving very, very slow. So in order to make our character moving faster, we just need to provide some constant here, so let's make it 3. It should be really enough there. Okay, so now it's moving faster. Well, I think we could make it moving a little bit faster again. So maybe let's make it 5. Okay. Okay, yeah, now it's perfect. So you see, like, now we can move along the map. We don't yet have collision detection, so we can walk through the walls. Okay, but anyway, we can cast our rays nicely. So obviously, if we step into the wall, that no rays are being casted because we hit the wall. We are currently in the wall, but otherwise we have this nice, fantastic rays being casted everywhere. And by the way, if you make the field of view equal to 360 degrees, it would be like a sun shining in like, well, let me probably show you this just for fun. It's not needed really, but just for fun I want to show you this little trick. Just has a nice visual effect. So let's say field of view is going to be I guess 2 pi, right? I'm very, very bad in math, so I'm not sure how many pi's do we need there, but yeah, here it is. So you see, like, well, I can go, well, no, actually can go side steps as well, but you see, like, now it's shining everywhere. So it's like a sun now. Okay, so I think this is just a cool effect. Okay, this is just a cool effect of having a sun shining everywhere, and it's really like some fractal here, so it's really nice. Okay, but obviously we don't need that, and let's drop back to the normal field of view of around 60 degrees, and this is how it looks like. Okay guys, so let's go for a very brief summary in regards to the practical application of the math being involved here, and walk through the places where this exact math is being used at. So the very first thing, so where we do use this math, when we draw the direction player is looking at, so we're using this exact math. So the idea of using this sine and cosine is just to get the target square, the target coordinate, target x and target y, for the current x and y. So let's say here is the current x and y, and here we have the target. So if we just have a look at our image, so red dot is the source xy, the player xy, the initial coordinates where the player is, and well, let me just disable this lines for a while, just to give it a bit more sense, just to give a bit more sense to this explanation. Okay, so the first application, so we need to get the coordinates of this particular point, so we call it target x and target y. Okay, so how to get this? In order to get the coordinate of this dot, it's changing, if we change in the player angle, so where we're looking at, we need to calculate dynamically the coordinates of this exact dot, right? And in order to do this, so there would be target x and target y. So in order to calculate the target x, we use this minus sign and the angle for our character, we're using the player angle in this case. Okay, and in order to get the target y or player y, target player y, target, well, okay, you know what I mean. Then we use player y plus cosine of the player angle. So this two little operations, like, I have no idea how this works in, like, under the hood. Okay, completely. I've been trying to learn that, but my mind is just exploding. But I just want to focus on how we can use this and why exactly do we need this. So so here is the formula to calculate the coordinate of this point, the x coordinate of this point. So like the x-axis and the y-axis. Okay, so to calculate the x-axis, depending on where the so this is the start x, and this is the end. This is the target x, the source x, the target x. Okay, and here we have the, well, probably pygame calculates from above, I believe. So here we have, I might be wrong though. Here we have the source y, and here we have the target y. So in order to calculate this, the source x, we need to say current player x minus minus sign of the player angle, okay, and to get the y we need to say player y plus cosine of the player angle, and then we just change the angle to get this target x, target y for the leftmost and the rightmost rays that coming from the player, and this limits the field of view. And then within the range of this field of view, we start casting rays one by one, and we're getting the target coordinate iterating over the depth. So starting from this point, then iterating a very small chunks. Well, I guess it's going pixel by pixel here, yeah, and until we hit the wall. And we do this for the number of casted rays. So in our case, we use 120 rays. So let's draw the rays again. So here we do absolutely the same math to get this target x and target y. So here we just do explicitly specify that we're looking for this target x and target y. Here they are kind of like embedded, but the formula is very similar. So the difference is that here, instead of multiplying by a single constant, because with a single constant we have just a line of a fixed length, okay, but if we do multiply by the depth, we make this line kind of growing iteratively, okay, and we draw in the line, so from the source square, here from the player x, player y, from the source coordinates, from the player coordinates to this target x, target y. And yeah, let's have a look at this beautiful rays one more time. Okay, so here we have the rays, so exactly the same thing, but done iteratively, and also we add the condition. So if we do hit the wall, then we just drop the array, so the coordinate drops, and we're not drawing the ray any further. So I hope that's clear. And the very last application of this exactly the same math is to move the character, not absolutely like only up or only down, but to move the character along the player's angle. So this kind of central line is not seen because of the rays, but it, you remember it's here, so we always move along the central line. And in order to do this, again, like we need, when we press the up button, we need to update the target x and target y, but in this case not for the ray but for the player itself. And exactly the same if we go back, but just with a negated offset. So this is what's happening right over in here. So we have exactly the same math being involved, but here we just use a fixed step. So it's literally how these values are literally how fast do we want our character to move on the map. Okay guys, so this is from my side. I'm sorry for this tutorial became like a little bit messy, and I wasn't that fluent, wasn't that smooth. But again, like I just wanted to walk through the development process of how it goes if you're a complete beginner and complete noob in math like I am, just to emphasize those possible potential pitfalls and showcasing those possible potential pitfalls, because it's really cool, like guy shows like line of code, and then it's just everything is working, and you think like, what the heck is going on here? Like you don't understand how it works. So I hope this tutorial gives a clue on how the development process of this sort of thing looks like, how to break this task down into the steps, and the most essential thing is to figure out how exactly this sort of math is used in 3 cases in particular: to draw the direction we're looking, to draw the field of view, and to draw to cast the rays iteratively, incrementing by the depth until it hits the wall, and how to make the character moving it along this way. So there's 3 use cases, but using exactly the same math every single time. Okay guys, this is it from my side. In the next video we'll finally draw a 3D projection, so it's only the matter of drawing a plane and like making it like from making it from flat, just try to kind of like rotate. So here we'll obtain the 3D kind of illusion of this sort of a thing. But the most important thing that this game is that the raycasting is literally a two-dimensional algorithm. This is the two-dimensional game. Even though we can obtain this projection, still we live in the two-dimensional world here. And when it comes to say collision detection, we'll implement this a little bit later. It's the same thing. So we just horizontally hit the wall, we need to break. Okay. So we horizontally hit the wall, we need to break. I didn't yet implement this. This is coming in the next tutorials. But really, we can cast in the rays in the two-dimensional space. So these are the exact rays that we're casting, and this is what gives the entire algorithm the name, its name. So we have this rays being casted from the player's perspective and to the outer space until it hits the wall. So this is so raycasting is a two-dimensional algorithm, but it can be turned into the three-dimensional illusion. So I call it illusion because we don't have any information about the Z coordinate. We don't have Z coordinate in our initial game. So this is the two-dimensional thing, and we'll use just some tricks to draw what they call a projection plane to display the 3D image of what's going on here. Okay guys, now this is really it from my side. I'm really sorry for this tutorial, it kind of takes a bit too long, but I really tried to make this as clear as possible. I hope it worked. So thanks for watching, until the next time, and take care.